Hello, my name is Cameron Wyzorek, and this is my Math 810 seminar presentation on the mathematics of musical temperament systems. I want to start by laying out the goals of the presentation, and then we'll get into the heart of the talk. For introduction purposes, I want to discuss some basic music theory terminology that we're going to be using throughout the presentation. So I'll introduce vocabulary such as what is a note, what is a semitone or half step, what's a sharp, what's a flat, how do we define an interval in music theory, what's an octave. So we'll go through some basic terminology. Then I'm going to get into the basics of piano tuning. So we'll talk about frequencies, we'll talk about beating, we'll talk about what a fundamental pitch is that a piano tuner would use to start tuning a piano. The next thing I'm going to be discussing is what's called just intonation, and that will lead into the heart of the presentation, which is going to be discussing the mathematics related to what are called equal musical temperament systems. The two main temperament systems that we're going to be focusing on are what are called the 12-tone equal temperament system, often abbreviated the 12-TET. We'll be discussing frequency ratios, how to name notes using the cyclic quotient group Z mod 12Z. We'll discuss computation of key signatures and enharmonic equivalence, and introduce some terminology called the dominant, the subdominant, and the circle of fifths. After a discussion on the 12-tone system, I will discuss the 19-tone equal temperament system, and we'll have a discussion about the dominants, the subdominants, and what's called the circle of sixths instead of the circle of fifths in the 19-tone system. So I'll offer some comparisons for how this system differs from the 12-tone system. At the very end, I want to offer some concluding remarks and some extensions, some alternative tuning systems, specifically Pythagorean tuning and logarithmic tuning, which are two specific tuning systems that do not use equal temperament. So we'll be able to compare and contrast a little bit. So to get started, I want to talk about some basic music theory terminology. The most basic concept in music is what's called a note. And all it is it's a symbol that corresponds to a musical sound. The letters used to name notes in the typical music theory system are C, D, E, F, G, A, and B. So on a piano, that would sound like this. This is a C, D, E, F, G, A, B, and then we're back to C, just a little bit higher. The distance between any two successive notes on a piano is what we call a semitone interval, or a half step is what it's also called. If you started a note and you raise a pitch a half step, it makes a note sharp. And if you lower a note a half step, it makes it flat. So for example, if I go from C and I go one semitone above it, that would be a C sharp. If I was to go from C and go down a half step, that would be a C flat. So it just depends on which direction you're moving a semitone, up or down. The number of semitones determines what's called the interval width. Some of the more popular intervals in music theory are the major third, which is 4 semitones. So for example, a C to E would be an example of a major third. If I go from C and I go up 4 semitones, sounds nice. That's a major third. A perfect fifth, we'll talk about why it's called perfect in a little bit. A perfect fifth is 7 semitones. So that would be like from C to G. If I go from C and I go up 7 semitones, 1, 2, 3, 4, 5, 6, 7, also sounds nice. That would be a perfect fifth. Just a couple examples of an interval width. An octave is what we call the collection of all 12 distinct semitones. So this is the point in a set of notes where things start to repeat themselves. They're just a little bit higher or a little bit lower. So for example, from C to C, it almost sounds like one pitch, but there's actually 2 notes being played, but they're both Cs. They're just 1 octave apart. They're 12 semitones apart. And 2 notes that differ by 1 octave are given the same letter, the same note name, but we use a subscript to distinguish what octave they are being played in. So for example, C sub 4, often called middle C, it's the halfway dividing point of the keyboard. That'd be a C4. C5 would go 1 octave higher. Still a C, but a higher pitch. So that would be C4 and C5 played together. Just to offer a visual in terms of the keyboard, The distance from any white key to any adjacent black key is a semitone or a half step. Also, you'll notice there's a couple spots within an octave where there are no black keys in between the white keys. So for example, right here, this is an E where my cursor is pointing. From E to F is also an example of a semitone, even though it's not going from white key to black key. Those two successive white keys form a semitone. I'm going to shift over just a little bit. My cursor is now highlighted on B. If I go from B to C, that is also a semitone. That's another spot within the octave where there's no black key in between those two white keys. And also outlined in the diagram, what I just played actually, C4 to C5, is outlined here. So you can count 12 semitones from C4 all the way up to C5. That would be the span of one octave. Okay, so let's talk about some piano tuning basics. Regardless of which tuning system is being used, there needs to be a baseline pitch. So when someone comes to tune a piano, they need to get started somewhere, and we call this a baseline pitch. So let's let F denote a function whose domain is the set of all musical notes, we'll call it N, relative to a particular octave, K. And the range of this function is going to be the frequency values that are assigned to that note, and we measure the frequency in hertz. So N, this set that we're defining, can take on any of the notes C, D, E, F, G, A, or B, and it could also take on sharp or flat values of those notes. So essentially you have 12 options, because there's 12 notes within the octave. And K can range from 0 to 8, since we're dealing with all of the different octaves on the keyboard. So 0 through 8. Standard piano tuning often assigns A sub 4, so it's within the same octave as middle C. This would be an A4. This is typically the first note that a piano tuner would use to start assigning a baseline frequency. Sometimes middle C is used as well, but for the sake of the presentation, we'll start with A4. And they like to assign the frequency value of 440 hertz to A sub 4 as a baseline for measuring other notes on the keyboard or on the piano. So how do we calculate other values of F? How do we determine whether other notes are in tune relative to A4? What we do is we count what are called beat rates when two notes are struck at the same time. And beat rates are basically these periodic small changes in intensity when two sound waves interfere with each other. So the two notes that are being played are going to have two different sounds, and we're looking at the intensity of those sound waves and the changes between them. And what the piano tuner is listening for is what's called beat frequency. And this is the rate at which the volume is heard, measured from the higher note to the lower note. And what the goal of piano tuning is we want to get that beat frequency to be 0 hertz, meaning that your ears can no longer audibly detect beats, essentially. So the goal is for the piano tuner's tuning fork to match the piano string in tune so that beats can't audibly be detected. And once that happens, the note is said to be in tune. Sometimes the goal when you're doing this tuning is to obtain pure whole number frequency ratios between two notes. And this is what's called just intonation. A lot of times choirs will do this. They like to be using just intonation to tune themselves before they sing. And the goal is to get any pair of notes to have a whole number frequency ratio. So for example, an octave is probably the easiest example to start with. An octave indicates a frequency ratio of 2 to 1. And oftentimes there's some Fourier analysis that can be done for this using sinusoids. So I have a couple visuals under here that I'm going to point out and what they represent. So if we look at the one on the bottom left, this would be the wave pattern for an octave. And the two notes that are being played would be the individual notes would be the red sine wave and the blue sine wave. And in the diagram on the left, the red sinusoidal wave has twice the frequency of the blue wave, hence the ratio 2 to 1. If you add the two waves together, that resulting green wave, it's the sum of those two individual sine waves, it's the interference of the two waves. You'll notice that it's a periodic function. It repeats itself and has the exact same pattern over and over again. Another example would be over here on the right. This is the wave pattern for a perfect fifth. I brought that term up before. A perfect fifth indicates a frequency ratio of 3 to 2. So in the diagram underneath here, still looking at individual sine waves here, the red and the blue, the red sinusoidal wave has 3 halves or 1.5 times the frequency of the blue wave. And if you take the interference of those two waves and you add them together, you'll notice that the green wave also has a periodic pattern, just like the original two waves did. So this is just two examples, an octave and a perfect fifth, just to give an idea of what we mean by pure whole number ratio. So 2 to 1, 3 to 2. And in general, if you take two individual sinusoids and you add them together and you produce that resulting wave, if that resulting wave is periodic, what that indicates is that there's a pure whole number ratio between the frequencies for those two sounds. And to your ears, what's going to happen is that sound is going to be musically appealing. So we like it when these two waves interfere together to create a periodic sinusoidal wave. But unfortunately, not all pairs of notes have frequencies that we can separate by these pure whole number ratios. It can often be very difficult to try to get every pair of notes on the piano into this whole just system. And so oftentimes we compromise a little bit, and the tuning that results in adjusting some of these intervals and tweaking them to try to get them as close as we can to this whole number ratio is what we call a temperament system. So it uses approximation to try to get things as close to pure whole number ratios as possible. The two main temperament systems that I want to talk about in this presentation are the 12-tone equal temperament system, the 12 TET, and the 19-tone equal temperament system, the 19 TET. So let's start with the 12-tone system. The reason that we call this a 12-tone equal temperament system is because we're using a tuning system where the frequency ratio for any two successive semitones, any two successive half steps, is 2 to the power of 1/12. And the reason for that is you take 12 notes in an octave, you split them into 12 pieces, each separation is 1/12 apart. So the frequency ratio would be 2 to the power of 1/12, or approximately 1.059. Now, due to string stiffness, that leads to small frequency changes due to the piano string stiffness. Each semitone interval we divide into what's called 100 cents. And the frequency ratio for any two notes differing by C cents is given by the expression 2 to the C over 1200. 1200 is coming from the fact that there's 1200 cents in an octave. Since each semitone is 100 cents times 12, you have 1200 cents in an octave. And you can see if we plug in 100 for C, 100 divided by 1200 reduces to a 12th. There's your semitone that we mentioned up at the top. Each set of successive semitones has a frequency ratio of 2 to the 1/12, as we mentioned on the previous slide. So let's bring back our 2 to 1 ratio for the octave and show that that actually still holds true in this system. Since you have 12 semitones in an octave, the frequency ratio of an octave would just be the product of every single one of those semitone ratios. So if we take 2 to the 1/12 and we raise it to the power of 12, since we're going across all 12 semitones to get up to that octave, doing the math there, we would be left with 2, or a 2 to 1 frequency ratio, as we saw in the just system as well. And so, sometimes you still get that pure whole number ratio. It's not that you have to approximate it all the time. This is a case where it does work. But, as we said, there is approximation. Not everything can be a perfect whole number ratio. We mentioned that in the just intonation system, a perfect fifth, or 7 semitones, has a frequency ratio of 3 to 2. Now, using this 12-tone system, we know that each semitone is separated by a ratio of 2 to the 1/12. And since we are looking at 7 semitones, we're going to raise that ratio to the power of 7, multiply it 7 times in a row. And that comes out to be 2 to the 7/12, which is about 1.498, just under 1.5, just under a 3 to 2 ratio. And so this is why we call it a perfect fifth, is it's just under a perfect whole number ratio of 3 to 2. It's pretty close. So for the next part of the talk, there's going to be a lot of discussion of modular arithmetic and how we can actually use some abstract algebra in order to do things with key signature computation and things such as enharmonic equivalence, dominant chords, subdominant chords. So we're going to be using a numerical system to name the notes that I want to introduce. You'll notice in the center of the slide, I have the octave on the keyboard laid out exactly as you would see it in terms of color on the keyboard. So the first white key would be C, then the first black key would be C#, so on and so forth until we arrive up at the last note in the octave, which is B. Okay, so this falls in line with how the piano is laid out. Each one of these is going to be given a number 0 through 11. So C is going to be given the number 0. C sharp is going to be represented by the integer 1. D is going to be represented by the integer 2. All so on and so forth until we get up through B, which is going to be represented by 11. Okay, so the same order they're listed here. Also notice that C sharp could alternatively be labeled as D flat. D sharp could be alternatively labeled as E flat. F sharp could be alternatively labeled as A flat. G sharp, I'm sorry, F sharp could be alternatively labeled as G flat. G sharp could be alternatively labeled as A flat. And A sharp could be alternatively labeled as B flat. They're in the same position on the keyboard. It just depends on whether you're looking up a half step or down a half step from a respective note. Likewise, C and B could alternatively be labeled B sharp and C flat. The underlying structure behind what we're going to be discussing is the cyclic quotient group, Z mod 12Z, with addition represented by modulo 12. This is the underlying algebraic structure that we're going to be using for this 12-note system on the keyboard. And everything is going to fall in line since we're working mod 12. That's why we're using the integers 0 through 11 to represent the keys in the octave. Once we hit 12, it starts over and we would just start again at 0. So for example, just to keep it basic to start with, what if we wanted to find the perfect fifth above a G using this ring structure? Well, we know from the previous slide, if we count here, G would be represented by 0, 1, 2, 3, 4, 5, 6, 7. It'd be the seventh note that I see listed in my octave. Okay. So it'd be given the integer value 7. And we know a perfect fifth is 7 semitones above that note. So what I would do is I would add 7 to that note G, which is represented also by 7. 7 plus 7 is 14. Since we're working mod 12, we subtract 12, which leaves us with 2. And n equals 2, if I look at my previous slide, 0, 1, 2 is represented by D. 0, 1, 2. So D would be the perfect fifth above G, and G to D would represent a perfect fifth. I will play it, and you will see that it sounds pretty appealing to your ears. Sounds nice. That would be an example of a perfect fifth. Now, the next thing I want to discuss is how can we actually compute key signatures using the 12-tone system, and specifically, how do we know, given a key signature, what notes are going to be sharp, and how do we know which notes are going to be flat? And it really it involves starting with the most basic scale in music theory, which is the C major scale, which involves no sharps and no flats. And it involves all the white keys in the octave and doesn't use any black keys. The C major scale is C, D, E, F, G, A, B. And using our integer representation mod 12 from the previous slides, this would correspond to the integers 0, 2, 4, 5, 7, 9, and 11. And it sounds like this. I'll play the C major scale just so you can hear it. Every single major scale is going to follow the pattern whole step, half step, whole step, whole step, whole step, half step, talking about the distance between tones. Remember, a half step is just a semitone. A whole step is 2 half steps put together. So that would be 2 semitones instead of 1 semitone. So if I start with a C major scale and I want to compute any other key signature, I can use the following algorithm. And I'm going to lay it out, and then I'm going to go through a couple examples for how to use it. The first thing you do is you identify the first note in the scale, which is what we call the tonic note, and we find its integer representation n, we'll call it n, working mod 12. Okay, so we just find the integer of the tonic note. We add it to the set D from the previous slide. Set D was the original C major scale. So I'm going to add the tonic note to every single one of these integers in set D. Reduce them mod 12. So if any integers are higher than 12, I'm going to subtract 12, make sure they're between 0 and 11. And then I'm going to sort the values in this set so that they're non-decreasing, so that they go from least to greatest. And we'll call this sorted set S star. The last thing I'm going to do is I'm going to subtract the original set D, the original C major scale, from my set S star. And we're going to get a new set called P. And this set P is only going to contain either the values 0 and 1, or it's going to contain the values 0 and -1. It's not going to have 1s and -1s at the same time. And what this represents is positive ones will indicate that that note is now sharp in the scale, and a value of -1 is going to indicate that that note is now flat in the scale. 0 means no change. It's the same note as we started with. So this algorithm, not only does it tell you how many sharps or flats you're going to end up with in a key signature, but it's going to tell you relative to the original position in the C major scale which specific notes are actually sharp and flat. So let's start with an example. Let's say we wanted to know what the A major scale is, or what notes are sharp or flat in the A major scale. According to the algorithm, the first thing we're going to do is we're going to identify the tonic note, which is A. And according to our 0 through 11 representation, A would be the 9th note in that octave. So N equals 9 would be my tonic note. What I'm going to do next is I'm going to add that C major scale, 0, 2, 4, 5, 7, 9, 11, to the tonic note. So every single one of these integers, I'm going to add 9 to. Here's my new set. Notice that 5 of those values are larger than 12. So I'm going to subtract 12 from 13, from 14, from 16, from 18, and from 20, so that I'm working mod 12. And those become 1, 2, 4, 6, and 8. 9 and 11 stay as they were. The next thing I'm going to do is I'm going to sort this set so that the values are non-decreasing. They're listed from least to greatest. 1, 2, 4, 6, 8, 9, 11. Call that set S star. And the last thing I do is I subtract the new set here, S star, minus the original C major scale. So I'm going to go element by element. 1 minus 0 is 1. 2 minus 2 is 0. 4 minus 4 is 0. So on and so forth until I get to 11 minus 11, which is 0. And we'll observe there's 3 1s in this set. Since they're positive, that tells me I have 3 notes that are now sharp. And specifically, according to the original set D's ordering, it tells me that C would now be sharp, F would now be sharp, and G would now be sharp, because C, F, and G were the positions in that original set D for that C major scale. So I have 3 sharps now, and I'm going to play the 2 scales just so you can hear the comparison. The original scale, C major, sounds like this. And the A major scale, it's going to still use the pattern whole, whole, half, whole, 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 half, but it's going to sound like this. So again, one more time. There's C major. Here's A major. You can hear similarities, but obviously different tones, and there needs to be some sharps now because we changed the tonic note. All the other notes stayed the same. Let's look at one where there's some flats. This is the E flat major scale. Spoiler alert, because it has a flat, you can probably predict there's going to be some flats in the key signature. Okay, E flat, if I look at the keyboard, here's C, 0, 1, 2, 3 would be my tonic note, E flat. I'm going to add it to the C major scale, 0, 2, 4, 5, 7, 9, 11. We'll notice that there are 3 values that are 12 or higher, 10, 12, and 14. So we need to subtract 12 so that we're working in Z mod 12Z. I'm going to sort the set so that it's from least to greatest, non-decreasing. So S star is 0, 2, 3, 5, 7, 8, 10. And then the last thing I'm going to do is I'm going to subtract the original C major scale. That's my set D right here. And when I go element by element and I subtract, as we predicted, this time I end up with 3 negative ones, so 3 flats. And specifically, order is preserved from set D. This was C, D, E is now flat, F, G, A is now flat, and B is now flat. So the 3rd note, the 6th note, and the 7th note are now flat. I'm going to play the 2 scales side by side so you can hear this difference now as well. Here's C major. It's the original scale. Here's E flat major. So one more time, C major. And here's E flat major. Same pattern of whole steps and half steps, different notes. We introduced some flats this time. The next thing I want to discuss is what's called enharmonic equivalence of key signatures. Two key signatures are said to be enharmonically equivalent if they contain different notes, but your ear cannot detect any perceived change in sound when those two major scales are played. So for example, because B and C flat are the same note on the keyboard, okay, it's B major is this white key, and it's a half step to the left of C, so you could also call it C flat. Because they have the same note name, they actually, when you play their major scales, they're going to sound the exact same to your ear, even though written out they have different notes listed. Same thing with C sharp and D flat. C sharp is a half step above C, and it's the same position as a half step below D, so you could call it D flat. Those two major scales to your ear, you won't detect any differences, but when you look at the actual key signatures, they're going to look very different visually. So audibly, no difference. Visually, there's a difference. And converting between two enharmonically equivalent key signatures actually can be done as an intermediate step in the key signature algorithm that we just looked at. So I'll show you at what point there's a tiny little change. So the change happens before you sort the set S to obtain S star. And here's how it works. Because we're working mod 12, we're allowed to add 12 or subtract 12 from any number that we want in our 0 through 11 representation. And so the way this works is that if we see the number 11 show up in our set S, we can subtract 12 from that value since we're working mod 12, and we obtain the number -1. If the set 0 shows up in our set S, because we're working mod 12, we can add 12 to 0, and we can replace that value of 0 with the number 12. Again, this all stems from the fact that we're working in Z mod 12Z. The rest of the algorithm is going to be the exact same. The new calculation of S star, we're still going to subtract the set D to obtain P, and it's going to produce an enharmonically equivalent key signature. So let's let P and P star just be the two final sets of sharps and flats for these two key signatures. One will be the original key, and the second one will be the enharmonically equivalent key. Without loss of generality, let's just say that P contains sharps, and let's say P star contains flats. We're going to define this double bar notation to be, we'll call it a modified norm. Typically, the norm of a set or of a vector is non-negative. However, because of the fact that we could be using -1s for flats, if we add up a bunch of -1s, we're still going to have a negative value. So we'll call it a modified norm. And really all it's going to be doing is it's going to be summing up the entries in our final set P and our final set P star. And the interesting thing is that the size of these two norms end up being congruent to each other mod 12, since we're working within that same equivalence class. And that's where the term enharmonic equivalence arises from. Because we're dealing within the same equivalence class, these two norms are actually congruent to each other in size. So start with an example. Let's look at the enharmonic equivalence of B major and C flat major. Okay? Again, if these two major scales were played, your ears would not be able to detect any differences, but one of them is going to contain sharps and one of them is going to contain flats. So what I did on this slide is I went through the algorithm from earlier to show the sharps that arise from the B major scale. So I took the tonic note 11, I added the C major scale, I there was no need to subtract 12 from anything here. Everything was already between 0 and 11. I sorted the set and I subtracted the C major scale, and we can see that C, D, F, G, and A, relative to the positions of C major, are now sharp. So keep that in mind for B major, 5 sharps. Let's say we want to compute the flats that are in C flat major. In order to find the enharmonically equivalent flats in the C major scale, we said that we modify the algorithm. One thing I had mentioned previously is that if the number 11 shows up in the set S, we can subtract 12 and replace that value with -1. So notice here in the B major scale, in my first step, I noticed that there was an 11 that popped up. So what I'm going to do is I'm going to replace that number 11 with -1, which I outlined here in red. And everything else stays the same. 1, 3, 4, 6, 8, 10, I didn't change. Notice the set coincidentally is already sorted, so S star and S happen to be the same set. And the rest of the algorithm is the exact same. I take the set, S star, I subtract the original C major scale, and element by element subtraction gives me -1 in every single position. So all 7 notes end up being flat if you view it as a C flat major scale. C, D, E, F, G, A, and B are all flat. So looking at the size of the norms, here's P. P was our final set of sharps for B major, and I count 5 ones. So the norm of P is 5. For P star, I count 7 flats. If I add up -1 7 times, the norm of P star is -7. They are enharmonically equivalent. Those 5 sharps and those 7 flats are congruent mod 12. If you were to subtract 12 from 5, you get -7, or if you were to add 12 onto -7, you would get 5. Within that equivalence class, those two are congruent, which is why your ear isn't going to perceive a difference in sound. It only looks visually different when we list out the key signature. Let's look at one more example. Let's say we want to look at the enharmonic equivalence of D flat major and C sharp major. So D flat major I've outlined on this slide. If you go through the computation, the set P ends up having 5 flats, and based on their positions, it's D flat, E flat, G flat, A flat, and B flat. All I did is I took the tonic note, added the C major scale, sorted it from least to greatest, and then I subtracted the original C major scale. So I got 5 flats, D, E, G, A, and B. Now I want to figure out, for the enharmonically equivalent key of C sharp major, what notes are going to be sharp. According to our intermediate step that I outlined, if the number 0 pops up in the set S, which it does right here at the end, then I'm going to add 12 and I'm going to replace that number 0 with 12, which I can do because I'm working mod 12. So I take 0, and you'll notice I made the substitution here in red just to outline which number got replaced. It was 0. Now it's 12. Now you see me. Now you don't. There's 12. I sort the set, which it's already sorted now. 1, 3, 5, 6, 8, 10, 12. So there's my new set S star. And to get the set P star, I subtract the C major scale, 0, 2, 4, 5, 7, 9, 11. Element by element subtraction gives me 7 positive ones, meaning every single note from the original C major scale is now sharp. C, D, E, F, G, A, and B are all sharp. So the norm of P, I counted 5 flats, so -5. And the norm of P star, I count 7 positive ones, 7 sharps. If you add 1 together 7 times, you get 7. So the norm of P star would be +7. Again, -5 and 7, when working mod 12, those numbers are congruent to each other. If you take -5 and you add 12, you get 7. If you take 7 and you subtract 12, you get -5. And your ears would detect no difference. In practice, where could this be seen? This is just an example of a composition by Liszt. This is the Hungarian Rhapsody number 6. Interestingly enough, the first 40 measures are composed in D flat major, and then measures 41 through 72 are composed in C sharp major. And remember, D flat major, C sharp major, enharmonically equivalent. So when listening to the piece, you're not going to detect any change in key signature just by listening. But if you look at the sheet music, here, everything is written in D flat. You can see all the little flat symbols. And then it changes tempo here, meaning how fast it's being played. It's now being played presto, which means it speeds up. And it's now being played in C sharp major, according to all the sharps here in the key signature. Visually different. If you look at the sheet music, it does look different now, but audibly the same. The only thing audibly you could probably detect difference is that it's sped up based on the presto marking. So just an interesting practical composition that uses this idea. So the next thing I want to do is look at some very specific interval ratios in the 12-tone system. And the first one I want to talk about is what's called the dominant. Now, everything related to these intervals is based on the tonic note. So just as a reminder, the tonic is just your first note in a scale. So whatever the name of the major scale is, that's your tonic note. The dominant in 12-tone equal temperament, the dominant is a perfect fifth, or 7 semitones above the tonic note. The key signature of a dominant key is always going to have either one more sharp or it's going to have one less flat than the original key. So for example, in C major, we have a tonic note of C, which would be n equals 0 according to our keyboard labeling from earlier. So the dominant key, if I add 7, 0 plus 7 would be 7. So the dominant key to C would be G, 7 semitones above. And this is also true. C major, we said, has no sharps. G major has exactly one sharp in its key signature. It has an F sharp. So that going from the tonic C to the dominant G raised the key signature exactly one sharp. Or it could work in reverse as well. Let's say you start with F major. F would be note number 0, 1, 2, 3, 4, 5. So n equals 5 is the tonic note. If you add 7 to 5, you get 12. But since we're working mod 12, subtract 12. And your dominant key, instead of calling it 12, would be 0, which represents the note C. So F major has one flat in the key signature, has a B flat. By going to the dominant key, you actually lose that flat. It makes sense because C major, we said, has no sharps. It also has no flats. So we lose a flat from going from F to C, going to the dominant. So why 7? Why is the dominant represented by 7 semitones above the tonic? It has to do with the idea of a multiplicative inverse working mod n. So just as a reminder from number theory or from abstract algebra, when you're working in Z mod 12Z, a value k such that the product of m and k is congruent to 1 mod n is what we call a multiplicative inverse of m. And we can write k as m inverse, working modulo n. Note that k only exists if m and n are co-prime, so they can't share any factors in common. So as a very basic example, if we're working within Z mod 7Z, let's say m is 3, and I want to compute the multiplicative inverse of 3 in Z mod 7Z. What I'm looking for is a number that I can multiply 3 by, so that when I divide by 7, I'm left with the remainder of 1. And there's formal ways that you can check this. This is just by inspection. This is small enough numbers that it's pretty easy to work with. It's easy to check that m inverse is 5, because if you multiply 3 times 5, you get 15. If you divide 15 by 7, 7 goes in twice to 15 with 1 left over. So 15 is congruent to 1 mod 7, which makes 5 the multiplicative inverse of 3 working in Z mod 7Z. So relating this back to the idea of our 12 TET, let's let n represent the number of semitones in an octave, and we're going to let n sub w represent the number of white keys in an octave. The dominant tone, which we're going to call n sub w inverse, satisfies the equation n sub w times n sub w inverse is congruent to 1 mod n. So this is where it relates to the multiplicative inverse. In other words, the dominant tone, n sub w inverse, it's the multiplicative inverse of the number of white keys in an octave. So let's actually compute what n sub w inverse would be in Z mod 12Z. We're working on the 12-tone temperament system. We said n is the number of semitones in an octave. Earlier we said there's 12 semitones in an octave, so n would be 12. N sub w represents the number of white keys in an octave. If you look at a typical piano, there's 7 white keys: C, D, E, F, G, A, E, and then we're back to C. Starts over. Okay. So 7 white keys in an octave. So we're looking for a value, n sub w inverse. This is going to be my dominant tone. I want a value satisfying 7, number of white keys, times this dominant tone, needs to be congruent to 1 mod 12. Again, by inspection, it's easy to check that 7 is going to be the magic number that works here. 7 times 7 is 49. If you divide 49 by 12, 12 goes into 49 4 times with 1 remainder left over. So my inverse, coincidentally, also happens to be 7. So that explains why in the 12-tone system, the dominant tone is going to be 7 semitones above the tonic. It's because it satisfies this equation, okay, for any temperament system. And we'll see in a little bit what it would be in the 19-tone system as well. The subdominant, it's the note expressed by the negation of the dominant, or you could think of it as taking n minus n sub w inverse. Subdominant just means 7 semitones below now instead of 7 semitones above. Sub means we're going down. Okay. The key signature of the subdominant key is always going to have one more flat or one less sharp than the original key. So completely flip-flop from what we said about the dominant key. The dominant key either gains a sharp or loses a flat. This subdominant key either gains a flat or loses a sharp from the original key. So in the 12-tone system, what would be the subdominant? It's the negation of the dominant. So if the dominant's 7, then the subdominant would be -7. Since we're working mod 12, you could also add 12 to that value and think about it as the number 5. So in other words, the subdominant, it's either 5 semitones above the tonic, or you could think of it as 7 semitones below the tonic. And this falls in line with what we said here. C major has a tonic note of C, so n equals 0. The subdominant key, if you either subtract 7 or add 5, you land at F. And you gain a flat when you go from C major to F major. F major has exactly one flat, B flat. The other way around, D major has a tonic note of D, so that's 2 in our representation. If you subtract 7 or you add 5, the subdominant key would be G, okay, which is the 7th note in the scale. And from going from D major to G major, you lose a sharp. The key of D has 2 sharps, an F sharp and a C sharp. The key of G only has 1 sharp in the key signature, which is F. So you're either gaining a flat in the first example or you're losing a sharp in the second example by going from tonic to subdominant. And visually, you can represent this idea with what's called the circle of fifths. It's an organized layout that shows the progression of key signatures from either 0 sharps to 1 sharp to 2 sharps to 3 sharps, et cetera, et cetera. Or if you go the other way around the circle, it shows you the progression of flats. If you read it clockwise, you're looking at the progression of dominant keys. If you read it counterclockwise, you're looking at the progression of subdominant keys. So what I mean by that, and this idea of the circle of fifths works for the 12-tone system. I'll show you a modified version when we get to the other 19-tone system. But looking at this, start at the top. I usually start at the 12 o'clock position here. There's C major, no sharps or flats in the key signature. If I go around this circle clockwise, notice that I'm going from tonic note to dominant tone. I gained a sharp. Let's say G is the new tonic. I go up another 7 semitones to D. I gain another sharp. So when you go clockwise around the circle, you're gaining sharps. You're going up to dominant tones. But if you go counterclockwise, C to F, we said F is the subdominant to C. Or if you go from F to B flat, you're going down 7 semitones. So that's the subdominant to F. You're gaining flats. So it just depends on which way you read the circle, okay? Clockwise or counterclockwise. But it's showing you that progression of sharps and flats based on the key signatures. Okay. So that kind of concludes the discussion for now about the 12-tone system. What I want to do at this point is I want to compare the 12-tone system of tuning to what's called the 19-tone, 19-TET, 19-tone equal temperament system. This is the most popular equal temperament system besides the 12-tone system. And the major difference is that instead of splitting the octave into 12 semitones, you split it into 19 semitones, so that the frequency ratio for any 2 successive half steps or any 2 successive semitones is now 2 to the 1 over 19 instead of 2 to the 1 over 12. So that ratio ends up being about 1.037. At the right, this was from around the 1920s. A man by the name of Joseph Yasser designed this hypothetical keyboard layout for this 19-tone system. Okay. You can see that the keyboard looks very different than the keyboard that we see nowadays that's tuned in the 12-tone system. But there's also extra note names that had to be introduced as well. So instead of just having C, D, E, F, G, A, and B, we have extra notes as well to make up for those extra spacings to get us to 19 tones. We have V, we have W, we have X, we have Y, we have Z. So there's extra keys, means there has to be extra letter names as well. So what would the dominant tone be then in the 19-tone system? We said that the dominant is going to be represented by 7 semitones in the 12-tone system. This equation still has to be satisfied for any n-tone system, 12, 19, 30, 50, whatever you want. this equation has to be satisfied. So let's plug in some different values now, since we're dealing with 19 TET, and figure out what the dominant tone would have to be. How many semitones do we have to raise above the tonic? Since we're dealing with 19 tones in an octave, semitones in an octave, N would be 19 now. N sub W is still the number of white keys in an octave. Based on the keyboard layout, let's go to Yasser's keyboard and count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then it starts over at C again. So there's 12 white keys in an octave. So we're trying to satisfy this equation. 12 times N sub W inverse needs to be congruent to 1 mod 19. Again, numbers are small enough by inspection. We can see that 12 times 8 is 96. 96 is congruent to 1 mod 19. Since 19 goes into 95, you'd have 1 left over to get you to 96. So in other words, remember, N sub W inverse in this equation represents the dominant tone. That tells me that in the 19-tone system, the dominant tone is 8 semitones above the tonic, whereas in the 12-tone system, it was 7 semitones above the tonic. So now it's 8. The subdominant is still represented by negative N sub W inverse. So remember, in the 12-tone system, the subdominant was -7, or it was +5. In the 19-tone system, since the dominant was 8, the subdominant would be -8, so 8 semitones below the tonic. Or since we're working mod 19 now, Z mod 19Z, I could add 19 to -8, and that gives me +11. So you have two ways of thinking about it. The subdominant tone is either 11 semitones above the tonic, or it's 8 semitones below the tonic. And this is all, again, this is coming from this equation right here, based on the 19-tone system now. This is Woo's updated keyboard layout for the 19 TET. It's just a slight bit different than Yasser's original layout. In the upper portion here, you can see that there's just a minor adjustment in white keys and black keys. This part looks just a little bit different, but the note names that Yasser originally used are preserved. So it's still using the exact same letterings from Joseph Yasser. We have C, V, D, W, E, F, G, X, G, Y, A, Z, and B. Okay, so this is just an updated layout. And you'll notice, here's the tonic. If we count 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7, 8. There's my dominant tone. 8 semitones above the tonic. And if I count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there's my subdominant. So we said 8 represents the dominant and 11 semitones represents the subdominant. So just an example starting at C as the tonic. Let's look at a frequency ratio comparison. So how would audibly, what are the differences going to be in terms of pitch? So let's just use C to F as an example. So here's a C to F interval in a 12-tone system or on a standard keyboard. It's the interval of a fourth. It's a perfect fourth. Okay. In the 12-tone system, we know that F is the subdominant of C. Okay. It's the interval of a perfect fourth, and it's 5 semitones above the tonic note. Since we're talking about the subdominant, okay, we said that would be 5 semitones. So the frequency ratio then would be 2 to the 5/12, which is about 1.335. In the 19-tone system, though, remember, previous slide, C to F is 8 semitone difference. That's the dominant tone, because we said that 8 was the dominant value in 19 TET. So now we're looking at 6, the interval of a perfect 6. There's 6 white keys between C and F. So 1, 2, 3, 4, 5, 6. 8 semitones above the tonic note in the 19-tone system. Look at the 19-key keyboard. That means the frequency ratio would be 2 to the 8 over 19. So this numerator here is telling us the number of semitones. Okay. So 8 over 19, this gives us 1.339. So they're close. Okay, they're starting to differ by about the thousandths place. And in just intonation, that was what we talked about at the beginning, where we try to get perfect whole number ratios. The frequency ratio for any perfect fourth, CF included, is 4:3. So it's about 1.333. So all three of these you can see are relatively close to each other, but they're using different tuning systems. And because in the 19-tone system, we are dealing with perfect sixths now instead of perfect fifths, in order to raise the number of sharps, we have this idea of the circle of sixths. So similar to the circle of fifths in the 12-tone system, we can describe the circle of sixths in the 19-tone system, since it takes the interval of a perfect sixth, or 8 semitones, to raise the number of sharps in a key signature by 1. So this is Wu's visual diagram of the circle of sixths in the 19-tone system. So what are some of the commonalities or shared characteristics between the 12-tone system and the 19-tone system? There are two of the only NTET systems whose dominant to tonic frequency ratio is nearly a perfect just ratio. So what I mean by that is in the 12-tone system, we saw the frequency ratio between dominant and tonic was close to a perfect fifth. It was 2 to the 7/12, which was about 1.498, nearly 1.5, nearly 3 to 2 just intonation ratio. In the 19-tone system, the frequency ratio between the dominant and the tonic, since there was 8 semitone difference, was a perfect sixth. It was 2 to the 8/19, which was about 1.3389, which is nearly a perfect 4 to 3 just intonation ratio. That would be about 1.333 repeating. Okay. And audibly, though, if you're dealing with the 19-tone system, because you don't see those extra spacings on the keyboard, you don't have those extra keys to see, it would be perceived as a perfect fourth in the 12-tone system, even though in the 19-tone system, it's a perfect sixth. So on the standard keyboard, you'd only see a perfect fourth difference instead of a perfect sixth. Okay, so tonic to dominant frequency ratio is nearly perfect. That's why those are two of the most popular systems. So they're the main attractors to the general dominant to tonic frequency ratio, 2 to the power of n sub w inverse. Remember, that's the number of semitones needed to raise the key signature by 1 sharp. That's the number of semitones for the dominant tone. N was the number of tones in the octave. Okay. And so 3/2 and 4/3 are those main attractors. It's the main reason why 12-tone and 19-tone are two of the most popular equal temperament systems in music. Okay, so last thing I want to do is just talk about a couple alternative tuning systems that don't use equal temperament, but still try to adjust as needed. The first one is what's called Pythagorean tuning, and the second one is what's called logarithmic tuning. So I want to start with Pythagorean tuning. This is similar to just intonation in the sense that the goal is to try to arrive at perfect whole number ratios between notes. But it's a little bit more focused in the sense that the dominating ratio in the Pythagorean tuning is 3 to 2. The goal is that you try to get all pairs of notes to be some multiple of that ratio, 3 to 2. So that's kind of the heart of this system. The major third frequency ratio is most notably close to just intonation using this tuning. The idea is that in music theory, you can build a major third by starting at a tonic note and going up 4 successive intervals of a perfect fifth. I'll demonstrate this in a second. Okay, so you go up 4 successive intervals of a perfect fifth. You do it 4 times. And then where you end up, you lower that note 2 octaves. And from tonic to final note is what we call a major third. So for example, let's just say I want to use a C to E. This would be a major third. Now, how can I actually get there? Start at C, and I'm going to go and do 4 perfect fifths. So my first perfect fifth would be G. Now from G, I'm going to do it again, G to D. There's my second perfect fifth. Now I start at D. D, go up 7 semitones. Another perfect fifth would be A. And then last one, it's my 4th round. I'm at A. I go up 7 semitones, a perfect fifth. I go to E. So I started at C. I went up 4 perfect fifths. I ended up at E, way up here. Last thing I got to do is I got to lower it 2 octaves. So down 1, down 2. And then I play them together. There's my major third. So the logic then would be, since I went up at the interval of a perfect fifth, which remember, 3 to 2 in just intonation, I'm going to multiply 3 halves to the power of 4, since I did it 4 times to get from here to here. But then I lowered it 2 octaves. So I also now have to multiply by a half 2 times. Okay? The reason I'm not doing 2 to 1 is because I'm going down an octave. I'm going to take the reciprocal and I'm going to use a half since I'm lowering the tone. So 3 halves to the 4th times 1 half squared tells me that this ratio should be 81 to 64. But in just intonation, we know a major third frequency ratio is 5 to 4. And if you multiply the numerator and the denominator by 16, it actually gives you 80 over 64. So the numerator differs by 1. The fraction differs by 1 over 64. The pitch gap is about 21.5 cents between this just major third and this Pythagorean major third. And that pitch difference is what we call the syntonic comma. A comma in general in music theory is just a pitch difference between 2 tones. But interestingly, the Pythagorean major third, it's still closer in pitch to the 12-tone major third. It's only 8 cents higher than the 12-tone compared to the just major third, which is 14 cents lower. So it's actually a little bit more off if you use the just major third. So that's one alternative tuning system that you can use that tries to still obtain these pure whole number ratios. On the flip side, we have what's called a logarithmic tuning scale, which does not try to arrive at pure whole number ratios. This was proposed by Robert P. Schneider. And the idea is to try to arrive at a scale that uses irrational valued interval ratios that fits the model of a 12-tone octave on a standard keyboard. And what's nice about this system is it doesn't compromise any change in standard musical notation. So the main idea is you begin with a fundamental pitch given by, really, you can use any note you want. If you wanted to use A4, like we mentioned earlier, when piano tuners start tuning, you could start with A4. But typically, at least for this logarithmic tuning scale, middle C is what Schneider chose. Middle C, because it just splits the keyboard in half, it's a nice place to start. And so you calculate this fundamental pitch, which we'll call F, by the standard frequency for middle C, 264. And again, if you wanted to substitute that frequency with whatever your fundamental note is that you're starting with, if you're doing A sub 4, you could do 440 like we talked about earlier. But let's use middle C, 264. And here's the key. You divide it by the natural log of 4. So this is giving rise to the name logarithmic tuning. This is about 190.4 hertz. Subsequent tones, okay, are going to involve this expression. So middle C is what we denote tone 4 star. The star is just indicating we're using this logarithmic tuning. So we'll call that note C star. C star is going to be middle C. And we're going to give it the value F, this 190.44, and we're going to multiply it by the natural log of 4 so that middle C is not compromised from standard tuning. 264 is what we want middle C to typically be. But this is where the logarithm comes in. Any note after middle C in that octave, the nth tone in that octave starting at middle C is expressed by the value F times the natural log of 3 plus n. All n represents is the nth tone in the octave starting at middle C. So if n equals 1, you would get F times natural log 4, which is middle C. That gives you 264 hertz. C sharp would be n equals 2. So you would have the natural log of 5 times F. And that's how you build your frequency values using this logarithmic scale. And this would work all the way up through the 12th note in the scale, which would be B. And then you don't need the list to continue on because this gives you the frequency value for the C4 to B4 octave span from here to here. Anytime you want to go lower than C4 or higher than B4, all you need to do is take the frequency value for the specific note in the C4 to B4 scale and multiply or divide it by the appropriate power of 2. Okay? So this really works for any note that you want, but if you want to try to go higher than that C4 to B4 octave, you're going to have to multiply by powers of 2 based on how many octaves you go up. If you want to go lower than the C4 to B4 range, you're going to divide by 2 a certain number of times, depending on how many octaves you're going down from that tone. And that just stems from the fact that an octave, again, has a frequency ratio of 2 to 1. Okay. Up an octave, multiply by 2, down an octave, divide by 2. Okay, so let's just do a little comparison. We said earlier that standard piano tuning assigns the frequency of A4 to be 440 hertz as a baseline measurement for tuning other notes. Let's see what that would actually be using this logarithmic scale. So if I wanted to find the frequency value of A4, it just so happens to lie in the same octave as middle C, which was our baseline for this logarithmic tuning. It would be the 10th note in the octave, so N would equal 10 in this case for the value A. It's tone 13 star. So I'm going to take F, that 190.44, times the natural log of 3 plus 10, natural log 13. Multiply that together, you get about 488.46 hertz. Now, compare that to standard tuning, 440 hertz. The frequency ratio between that 488.46 and that 440 is about 1.11. And if you set, earlier we said that you can use this equation to look at frequency ratio. Let's see how many cents they actually differ by. 2 to the C over 1200, right? 1200 cents in the octave. Set it equal to 1.11. If we take the log base 2 of both sides and we multiply by 1200, we would actually obtain that this C value, the number of cents the two tones differ by, is about 181 cents. Now think back to our conversation from earlier. We said that the semitone difference between any two successive notes is 100 cents. This is almost 200 cents. So this is almost differing by 2 semitones apart from the 12-tone system. It's actually a pretty big difference. But if you train your ears to listen to this, you get used to it. So why would you want to use this? If it's compromising 2 semitones, what are the benefits? 2 things. For one, you have more tones to work with within a scale. You get more musical creativity because of the subtraction property of logarithms. Let's just say you take 2 tones that are in this logarithmic scale, X and Y. Because when you subtract 2 logarithms, it becomes the log of their quotient. So long as these 2 values, X and Y, divide to give you an integer, that ratio of those 2 tones also would be a tone in this logarithmic scale. That logarithmic property is still preserved. So it gives you more tones to work with and more musical creativity to create your compositions. Okay? More tones. Thumbs up. The other thing is, people have said that this musical tuning system leads to more elegant and environmental sounds, kind of more esoteric sounding music. So again, allows you to have some more advanced musical creativity. So just a couple alternative tuning systems. Okay. So that kind of concludes the presentation. We started the presentation by looking at just intonation and some of the basics behind piano tuning. We saw how it's hard to obtain pure whole number ratios, so we had the need for this equal temperament tuning, and we looked at the 12-tone system, we looked at the 19-tone system, and we compared and looked at why these are the 2 most popular types of tuning systems used to tune the piano. And we concluded by looking at a couple alternative tuning scales, the Pythagorean tuning and the logarithmic tuning scales. I'd like to give special thanks to my seminar advisor, Dr. Daniel Miller. Thank you for all of your feedback and all of your help throughout this process. It was a pleasure working with you. I'd like to thank my colleague at Libertyville High School, Matt Karnstedt, for giving me inspiration in terms of trying to find a topic that I like to work with. And I really do thank you, Matt, because I really did get into this topic and I really enjoyed learning about this, and it's given me a bigger appreciation for the piano and the music theory that goes into the piano. I'd also like to thank the 2 students who gave me peer reviews, my fellow Math 810 students who offered me feedback from my draft to revise for this final presentation. It was very much appreciated and helped make the final presentation stronger, so thank you for that. And I would like to end with first I'd like to state that this is my works cited. These are the references that I used to help me with the presentation. And I think it would be beneficial to end with a cheesy piano joke. Without the piano, life would be flat. And I'm even wearing the t-shirt. Hey, that concludes the presentation. I'll just lead or end the presentation with a nice little melody so you can hear some music. Thank you very much for listening.